Good afternoon to all of you, and welcome to the October 2014 Smart Grid Educational Series Seminar, live here from the UL facility in Fremont, California. This is Irfan Ibrahim, your moderator. Welcome to this exciting forum. We have three wonderful speakers today. Craig Lewis is the Executive Director of the Clean Coalition. And then we have Andy Tang, who is the Senior Vice President at Greensmith. And then we have Bernie, who has so many titles in so many organizations that it would take a special Smart Grid Educational Series just to go over that. But he is involved with NECA and IBEW and does sustainable stuff. And that's where I'm going to leave it at. And when Bernie comes on, he can explain more about his various skills in this business. Let me just start this seminar, by talking a little bit about why this subject is so important at this time. I have alluded to it in previous seminars that I've moderated, but because the audience keeps changing, I feel that it's time for a little short review. So let's take it from the top. The Kyoto Protocol ask us to reduce the carbon footprint by 2050 to the extent of about 90% relative to, some people claim 1990 levels, some claim 2005 levels. So imagine if we want to reduce our carbon footprint by that much by 2050, all sectors of the economy have to participate. And the Kyoto Protocols address the 37 industrialized nations specifically in asking us to reduce our carbon footprint because it's very, very large. Okay, so if you want to reduce your carbon footprint by that much by 2050, we're already in 2014. And there's still a lot of coal, and there's still a lot of natural gas, and there's still a lot of transportation with fossil fuels. So the carbon footprint is pretty large. And it doesn't go away just by wishing it away. You have to have credible options. And when I say credible, I mean maintaining the same standard of living and improving over time as we expect societies to evolve, while keeping the cost of electricity and the cost of transportation affordable, and also improving the job opportunities and the overall economic prosperity. So we're talking about an operations research, a linear programming problem with a lot of constraints. And the way out of these constraints is through innovation. But when I say innovation, I'm not just talking about in technology. I'm talking about innovation in business process and innovation in policy, collectively working together to achieving this. So in the area of energy, I'm talking about now in production of electricity, we found that in the order of carbon footprint entities that are involved in generating this carbon footprint, transportation was the largest one, utilities came second, and then there are other sectors. So imagine if we move from this traditional grid that we have today to a smarter grid, which can invoke renewable energy like solar and wind with the use of storage, with the use of demand response, with the use of energy efficiency, we could potentially reduce the carbon footprint while keeping the cost of electricity affordable and creating jobs in the economy. And so this whole exercise around smart grid and enabling renewable energy and electric transportation is all an attempt in achieving those macro goals. So it's important for us to keep reminding ourselves why we're doing this and why this is not a nice to have, why this has become an absolute necessity over the next 10 to 20 years. The main reason is that a lot of the centralized generation plants, the fleet is getting old, and they're being replaced increasingly by renewable energy and other forms of distributed generation. So we cannot continue counting on the traditional grid in the way it used to work with this increased move towards distributed generation. It requires a rethink on how we produce, distribute, and use electricity in the future. So keep that in mind. Now, with this distributed generation and the smart grid architecture, let's go a little further and ask, what do we need to do? We need to definitely empower the customer to have choices. We need to have, in the regulatory framework, facilities, both financial and technological, to enable customers and service providers to participate in this business. And we need vendors to produce innovative technologies at a price point that makes the electricity affordable from those sources while giving them a fair return on their investment. So to address all of these issues, I've brought 3 experts who are going to take this problem and address it from different ways. At the highest level, at the policy level, and at the level of initiatives in the private sector. We have Craig Lewis, who's going to talk about community microgrids and other state-level initiatives. We're going to have Andy Tang from Greensmith, talk about some of the technological barriers around distributed generation and how storage is helping address some of those. And then we're going to get into the implementation aspect of it. And Bernie is going to talk about some of the standards that the National Electric Contractors Association, NECA, is developing around standards for installation of storage systems and distributed generation, something about the training around that and how you get the installers trained, and then also about just the general evolution of the standards work. So as you can see, between these 3 speakers, we have quite a diverse perspective on this subject. So with that, I'd like to welcome Craig Lewis, our Executive Director of the Clean Coalition, who's going to share with us some of his thoughts on the policy and also some of the initiatives. So Craig, I'd like you to come and sit at my seat here, and then I'll show you how to drive this, and then you will just drive it. So welcome, Craig. And I'm going to move this into a full mode. And I believe by just pressing page up and page down, you can move up and down.
Okay, great.
There you have it.
Great. Thank you, Irfan. And it's a pleasure to be here. I know that the topic today is energy storage, and to the comments that Irfan was just making about the bigger picture, the energy system. The Clean Coalition does a lot of work in this area called community microgrids. And this is about really the future energy system and the future energy system that we actually really need. And you could call it distributed energy resources. Other people probably call it different things. But basically, it is a renewables-centric ability to get local energy sources to keep all the vital grid services in balance, and the vital grid services being power, voltage, and frequency. You get right down at the bottom of it, that's it. So making this happen, of course, is going to require a sea change from the way that we've done things historically on the electricity system. And the way to get from where we are today, which is a set of systems that are really based on central generation, fossil fuel power plants, to a situation where we've got distributed energy resources, where energy storage is going to play a very significant role in that. We've got a lot of policy territory to cover. Lots of things have to change. So I'm going to be talking about it from that type of perspective. And I'm going to try my best to not get bogged down in a whole lot of details, because this subject matter can get very wonky. And on the policy side, it can get very technical on the technical details. I'm going to try to stay at a high level, and then in the Q&A session, we'll do deep dives, however deep everybody wants to go. But I'm going to try to give you some idea of where the policy situation is right now, where we've got the most important elements of the policy change that need to happen. And then I'm going to talk about a few real-life examples of how energy storage can play a very significant role in the energy future, and kind of wrap it up with those real-life examples. So let's see, page down. Here we go. So in order to really understand where I'm coming from, I think it's important for you to understand a little bit about the Clean Coalition. So I'm going to take just a couple minutes and tell you the Clean Coalition has a very specific mission, and the Clean Coalition is a nonprofit organization. So our mission is to accelerate the transition to renewable energy and a modern grid. And we do that by applying very deep technical, policy, and project development expertise. So we come at this, we're not a typical nonprofit. We are coming with very deep expertise for the things that need to come into play here from a policy and a technical standpoint, and knowing how to go through the project development process. I was a renewable energy project developer and got the very first solar project through California's renewables portfolio standard solicitation process. And I've been involved in several dozen renewable energy projects, so I know how this game works from a project developer standpoint. And it's a tough game, mostly because the policy is structured for the old way of doing business instead of the new way. We're very fortunate, the Clean Coalition is very fortunate to have a number of luminaries on our board of advisors. We hand-selected these people, and they've been very helpful. Some of the folks you would certainly recognize, people like Governor Bill Ritter, former CIA Director Jim Woolsey, folks like Amory Lovins and Terry Tamminen, and lots of other folks that we're very thankful to have their guidance. In terms of the overall objectives of the Clean Coalition, they're really summarized on this page. First of all, that by 2020, at least 80% of all new energy generation will be coming from renewable energy sources. And at the same time, at least 25% of all new energy generation will come from local renewable energy sources. And we carved this out because the 80% renewable energy sources, I think, is actually really achievable. The 25% local renewable energy sources is a lot harder, And the reason for that is it's more expensive to do local renewable energy projects than it is to just do the massive out in the middle of the desert renewable energy projects. And more important and worse for achieving that 25% goal is that the world doesn't yet fully count for the cost of transmission. Transmission is a massive cost. It adds 3 cents per kilowatt hour to every kilowatt hour of electricity that you consume here in California. We need to make sure that that is accounted for when we're doing the comparison of local versus central renewables and any other type of generation. If you need transmission, you need to make sure that it's properly charged for the real costs associated with it. And so what the Clean Coalition works on every day is putting the policies and programs in place to make sure that the 80% and 25% objectives are achievable. There's no way this is going to be a step function that miraculously, starting in 2020, we're just going to be getting, massive majority of our energy from renewables. This has to be, and we're already on a very steep curve between now and 2020. So Clean Coalition is working hard every day to put the policies and the programs in place to make the 80%, 25% renewables objectives possible. All right, if you're going to put the Clean Coalition's view of the world into a single picture, this is the picture. So what you see here is a distribution grid. Everything on this picture is within the distribution grid, meaning you're close to where people live and work. You're where wood power poles serve the electricity. There's only one thing on this picture, so I misspoke. There is one thing on this picture that is on the transmission grid, and it is the steel transmission tower that feeds the lines into the distribution substation. Aside from that one steel power tower, everything on this picture is on the distribution grid. So we've got the local generation, most of it being local renewables. We do have a fuel cell and microturbine there, which could conceivably be powered by biopower, but more realistically in today's world, those devices are going to be powered by natural gas. So there is a role for natural gas. If we're going to have natural gas as a bridge solution, I want to see it in really small chunks at the local level so we can replace it a lot more easily than pumping billions of dollars into central power natural gas plants. We see electric vehicles and demand response is a big part of the picture here. And also the secret sauce of tying all these resources together is the monitoring communication control solutions. Call it microgrid controller, call it lots of names for it. But at the end of the day, it's the technologies and the solutions that do monitoring, they communicate, and they control. So monitoring, communication, control. Now, our policy focus as the Clean Coalition as an organization is focused on 4 key areas. And we believe that these 4 areas represent the biggest hurdles to this transition to the distributed energy resource future. Those are distribution grid planning, procurement, and when I say procurement, I mean utility buys. They're either buying the power on a per kilowatt hour basis or on a VAR basis, whatever, a VAR hour, or they're actually just buying the actual capital expenditure, whether it's a battery or something else. When I say procurement, I'm talking about utility buys it. Interconnection. Now, on interconnection, I have a note there in parentheses that says utility pays. We can make interconnection a whole lot easier, and we can give utilities an opportunity to make some money and thrive in this distributed energy resource future by allowing the utilities to pay for the network upgrades associated with distribution grid upgrades in the same way that they currently pay for transmission grid upgrades, but are disallowed from doing that at the distribution level. And then monetization. When I talk about monetization, it's similar to procurement, except the big difference is who's paying for it. When I talk about monetization, I'm talking about open market transactions. So in California, these are the transactions that basically get settled at the CalISO, at the California Independent Systems Operator. All right, I'm going to just give one quick commercial here because there is a organization that the Clean Coalition is helping to form called the Dynamic Grid Council. And the Dynamic Grid Council is about getting the policies right and making sure that the policymakers understand and that the utility executives understand that there are technology and solution providers out here that can bring this future that the Clean Coalition is promoting, and we can let the policymakers know what are the obstacles, what are the policies that we need to put in place, and what are the benefits from getting there in the fastest possible time frame. And also working with the utilities to establish deployment programs, demonstration deployment programs, so that there are near-term market opportunities for this future. Most of the companies that are in this space, I imagine there are some of you are, and lots of people on the line, I'm sure, are distribution energy resource suppliers. You have solutions you want to sell. If we don't have some near-term market opportunity for you, those companies are going to die. They're going to shrivel up and die. So we've got to make sure we've got near-term opportunities through demonstration programs, and then we need to make sure that the market is right in the medium and long terms by getting the policies in the right place. All right. So when I start really getting into the topic of the discussion here around energy storage and the other distributed energy resources that all need to play together to make this future happen, this community microgrid future, it's really important just to get down to the basic fundamental level of how the grid works. And when you do that, when you tear away all the complexities of market structures and all the fancy language, the resource adequacy and ancillary services, most people, they've heard the term ancillary services in this business. 9 out of 10 of those people have no idea what it means. So at the end of the day, when you wipe away all the complexity of the fancy language and market mechanisms, there's 3 things that matter on the electric grid. You need to balance power, voltage, and frequency at all times. And that's it. It's really as simple as that to describe. Now, doing that is tougher, right? It's a lot tougher than just saying it. But if we focus on what you need to accomplish rather than getting everybody confused with everything else, all the fancy market mechanisms and complex language, then we actually have a hope of getting to a future set of policies that are going to bring those three vital grid services in a very efficient way that create a level playing field and allow solutions like energy storage to maximize their potential and to get compensated in a fair manner for bringing the solutions that they do. So it's important here in this table, each one of these vital services, power balancing, voltage balancing, and frequency balancing, I've got a key metric next to each one of those. And that key metric is really important to keep in mind because most people only think about power balancing. And power balancing is really the easiest of these three to do. But it's unfortunately the only one that most people spend any time thinking about. So when you're thinking about power balancing, you need capacity of power needs to match what the demand for power is going to be at any instant in time. Okay, that's the easy one. Voltage balancing is about having the availability of bars available to provide voltage support. And when you talk about bars, you're now talking about location is the most important metric associated with voltage balancing because bars decay rapidly over distance. So much more rapidly than real power does. In capacity balancing, power balancing, that's about balancing kilowatt hours. The voltage balancing is about balancing bars. And the location of a bar is extremely important because the decay is very rapid. And most voltage imbalances are caused by loads. So you want to have bar provisioning right on top of load. That's the most important thing when it comes to bars, getting those bars very close to where loads are. Yes, and what I'll do is, well, maybe Irfan's going to help me define that, but I've got a slide later on in the presentation that I can bring up.
So VAR stands for voltage, ampere, reactance. And whenever you have capacitive and inductive loads on a circuit with alternating current, you have it's a vector. The voltage is actually a vector. It has a real component, which is the resistive part, and an imaginary component, which comes from inductive, which is positive, and capacitive, which is negative. And so when we talk about VAR support, we want to get the voltage vector as close to the real axis as possible so that we have unity power factor. That means the amount of energy that's being put into the system is effectively being converted into useful energy and not in warming up the atmosphere.
You know, and I'll just add to that, and I'm not sure it'll be any simpler than what Irfan just said. Not that I thought that was simple, but you know, a VAR is basically a phase shifted. The power is phase shifted, so it's just moving the phase on the energy around. So again, I don't know if that simplifies anything for you, but if I have a chance at the end, I'll go to one of my backup slides. And by the way, these slides are going to be available for folks, and I'm going to present about 15 slides, but there's another 30 or so slides that go into lots of details, including explaining the VAR situation. So we talked about power balancing, voltage balancing, and frequency balancing. When it comes to frequency balancing, the vital metric is speed. You want to be able to react to that frequency of deviation fast, and that will save you from having to throw 10 times more resources at it. So if you can respond within a sub-second time frame for a frequency deviation, you're going to need 1/10 the amount of resources to resolve that issue than if you waited 3 seconds. And even 3 seconds, we're out of the time frame that a natural gas power plant can react. But we are in the sweet spot of the distributed energy resources like advanced inverters, energy storage, and demand response. So I like to go through this slide in real care, with real thoroughness, because these are the types of things most people don't understand, including utility executives and policymakers. And if they don't understand this, then how are they going to put policies in place that reward location and reward speed? Because that's what we really need to reward. And unfortunately, the things that get lots of traction, and everybody in California and heck, the rest of the country and even other parts of the world are talking about, is the duct chart. Well, the duct chart only deals with power balancing. The real issues, way bigger issues than the duct chart issues, are balancing voltage and frequency. So we've got to make sure we're focused on the right things, and that's what I'm trying to get across in this slide. All right, so we talked about the Clean Coalition's focus on distribution grid planning, procurement, interconnection, and monetization. And really all of that is around distributed energy resources, from local renewables to energy storage, demand response, monitoring, communication control, et cetera. So the distribution grid planning, this is probably going to sound a little strange that right now the distribution grid is not planned. The utilities don't have plans for the distribution grid. It's a very reactive process. And on the transmission grid, it's not the case. The transmission grid is, relatively speaking, well planned. But as soon as you get from that distribution substation on down, there is very little planning going on. And yet it's billions of dollars a year just in California that are spent making upgrades on the distribution grid, even though it's not planned. So we've got to do a lot more planning on the distribution grids, and thankfully there is some real movement in this direction. There's a bill that passed last year, AB 327, that requires the utilities to put distribution resource plans together, or at least proposals for those plans, by the middle of 2015. This is the distribution grid planning requirement is something that the Clean Coalition worked for multiple years to get done. We ran bills in 2012 and 2013, or excuse me, 2010, 2011 and 2012. We had dedicated bills to deal with this. We didn't get it done until 2013, and only then it was jammed into AB 327, which was first and foremost about net metering 2.0. But fortunately, from my point of view, the most important thing that came out of that bill is that we finally got the distribution grid planning requirements on the utilities here in California. Also, Southern California Edison has a preferred resources pilot that's going on. It's very exciting. Edison is taking a very concerted approach to understanding how we can resolve the issues associated with SOMs from distributed energy resources rather than relying on the same old way of doing business. And the Clean Coalition is very, we're very happy that we've been working closely with Southern California Edison on the preferred resources pilot, and we're looking forward to much deeper collaborations with them on that. And then in New York, I think everybody has probably heard by now of the Reforming the Energy Vision that's going on in New York. And New York, after Hurricane Sandy, they didn't have the luxury of just sitting down and proactively thinking this stuff through, and they're reacting to a changing reality that they're dealing with out there on the eastern seaboard. And so they're very serious about making sure that they're getting much more resilience built into their grid. And they see community microgrid concepts as being fundamental to that. Get the energy locally so you can keep the lights on in those local communities rather than having the storm take out a big transmission line or a big power generator and having huge swaths of their service territories knocked out simultaneously for multiple days and even weeks. Okay, so we talked about distribution grid planning, interconnection. Interconnection is the trump card that the utilities have. If the utilities do not want your generation or your resources on their grid, guess where they're going to kill you? It's on interconnection. So, because you will have to go through the utility to get interconnected to the grid. We need to streamline the process. We need to add certainty to the process. We need to give the utilities an incentive to participate. And when I talked earlier about utility pays, that is a really important incentive to the utility. They get to make the capital expenditure, which is the way that they get to make profit. They get a guaranteed rate of return on capital expenditure investments. So we've got to give them opportunity for that, because as we get to more distributed energy resources, guess what, folks? The utilities have a lot of disincentives not to like that world. Most importantly, they miss the opportunity to invest in transmission. And we've got to give them something to help make up for those losses. Otherwise, they're never going to willingly move away from that central generation model. And interconnection is really important, not just for energy storage, but it's really important for advanced inverters. And advanced inverters, when you take energy and you connect it to the grid, you have to have an inverter there to make that connection. Now, inverters are capable of provisioning things like reactive power, even though we haven't used them for that up to this point in time. But they have that capability, and we need to harness that capability, because an advanced inverter provisioning reactive power means that we now have reactive power voltage support happening close in to where you need it, on the distribution grid, close to where the loads are. And the loads are what drive the requirements for voltage support. So getting interconnection capability for advanced inverters is very important. Luckily, the CPUC is really moving aggressively with respect to the advanced inverters. And like I said, the advanced inverters are attached to the energy storage devices. So every time you have energy storage connected to the grid, you have inverters there. So we have this opportunity to use the inverters in combination with the energy storage. And then that combination, energy storage can do everything. They can balance power, voltage, and frequency. And then, of course, the energy storage in and of itself is being treated separately as an interconnection, from an interconnection standpoint. And again, the California regulatory bodies are doing some really good work. The California Independent Systems Operator has an effort going on that's referred to as GDAP, or GDAP, G-I-D-A-P, and it stands for Generation Interconnection. 5 minutes more. Okay. Sorry. Well, the Cal ISO is doing good things, and so is the CPUC through the Rule 21 proceeding. And I think that we're going to see some very good outcomes on interconnection, although the big one is allowing the utility to pay, which gives the utilities incentives, and it also takes away one of the biggest barriers to renewable energy and distributed energy resource project development, which is the way that interconnection is treated right now, where the developer pays, has to gift it over to the utility when the upgrades are done, and then has to pay tax and ongoing maintenance on it. And it's really complicated, and it's unnecessarily complicated. We could easily just get rid of all this nonsense by allowing the utility to pay for it, which is exactly the way it's done on the transmission grid. Procurement and monetization. We've got to establish pathways for the distributed energy resource owners to be compensated full value for their services. And when I talk about DER, I'm talking about demand response, energy storage, advanced inverters, and I'm also talking about opportunities for property owners. We've got to get property owners into the game, and so ability for property owners to either develop these projects themselves and own them, or to allow third parties, whether it's a utility or another third party, to come in and own them. But they've got to have a place to site these solutions. Got to get them into the game. I'm going to kind of rush through this because I'm down to just a couple of minutes, and I still have a few slides that I think are really important for folks. But I want to talk about the real-life solutions that are happening. So this, the Clean Coalition has an initiative called the Community Microgrid Initiative, where we work with several utilities around the country, including with PG&E up in San Francisco, and also the Water and Power Authority in U.S. Virgin Islands. So this picture is from the U.S. Virgin Islands, and what we've done here is you see the island of St. John. We've taken the entire island of St. John, and we've shown how we get 25% of total energy consumed from local renewables, which means at peak time of the day, which is one of the pictures here, you're getting more than 100% of the energy consumed on the island of St. John is coming from local solar. And that's exactly what we're seeing in this picture. What you see, the trace lines are the feeders that come out of the substation. The substation's on the left-hand side, and then you got the feeders that come out across the island over to the right-hand side of the island. And what we did here is we stacked this up with enough local solar to get to over 100% of total energy consumed at the peak time of the day. So we're actually back-feeding back to transmission, and the clean solar power is going back over to the island of St. Thomas, which right now provides 100% of the energy for this island of St. John. But at 6 a.m., the solar is not operational. The sun's not operational. You have no voltage issues on those feeder lines. But what happens at high noon, if you haven't done anything other than deploy the solar with unity power factor setting, which means it's just pumping out 100% kilowatt hours, you have a situation where the end of your feeders are actually offline. They are out of boundaries, out of the allowed voltage boundaries. And then you have other parts of the feeders as you get closer and closer to the substation that are close to going offline. What happens with a single solution, and that single solution is simply turning on the reactive power provisioning functionality of every inverter that's sold in the world today, and set it at a 0.9 power factor setting, which means that now those inverters can provision some reactive power in addition to just regular kilowatt hours. And we have a situation where the grid looks exactly the same as it did at 6 a.m. before any solar was being generated. So there's some very low-hanging fruit out there when it comes to distributed energy resources, and we need to harness that. I'm going to talk very quickly about the duck curve, the duck chart. Is it real or is it a decoy for natural gas? You know, if you really listen to the people who talk about the duck curve relentlessly, you can almost always trace it back to a natural gas provider. So there are some real issues here with power balancing, right? Most importantly, the ramping requirements that you have in the morning and in the afternoon, which those issues get worse and worse till we get to about 2020. Those are real issues. We've got to deal with them, but it's not rocket science, folks. Oh, my slide's I was supposed to have another slide in here that showed energy storage combined with some other solutions flatten the duck. So we get from a situation that looks kind of scary, if you actually know what you're looking at in this chart, to one it's actually less ramping requirements than we have in the grid today. So you bring the right solution set, and guess what? The duck gets flattened, and we don't have to worry about it anymore. Replacing songs. So hopefully everybody knows what San Onofre Nuclear Generating Station is. The folks who had to go deal with this in a hurry, mostly CalISO and the utilities and the CPUC, they basically came up with the grand solution of the main thing we need to go do isn't balancing power. So with songs, it was not balancing power, it was balancing voltage. So it was a reactive power requirement, not a real power requirement. And the solution that got jammed down everybody's throat was 2 synchronous condensers and a bunch of large capacitor banks to the tune of about 400 megabars of reactive power. Now, we could get to that exact same level of reactive power very simply by deploying local renewables and/or energy storage in a level of about 800 megawatts, which is easily done given the amount of resources that have been bid in to Southern California Edison and into SDG&E and into LADWP. We can get to 800 megawatts in a very straightforward manner. And simply turning on those advanced inverters with a 0.9 power factor setting, we get to that exact same 400 megabars, except we can do it much more efficiently because we'll be right on top of those loads where the bar requirements are driven from. rather than being out interconnected to transmission and having a whole bunch of decay before you actually get those bars to where you need it. Oh, this is, my slides were out of place. So this is the flattened deck curve. Wanted to just really quickly touch on the Hunters Point Community Microgrid project. So this is a project that the Clean Coalition is doing in partnership with PG&E. The goal is to show how we can get to 25% of total energy consumed within the Bayview-Hunters Point neighborhoods of San Francisco. This is 20,000 customers. It's about a 7-8 square mile area, and it's an average load going through that substation of about 35 megawatts. It's a substantial substation. And we're showing how we can get 25% of total energy consumed from local renewables, while at the same time maintaining or even improving grid reliability and power quality. This is a showcase project. PG&E has been a tremendous partner on it, and we are thrilled to be coming to the conclusion of our grid modeling and analysis phase, and moving into the phase of figuring out how we're going to actually go get this project deployed out there over the course of the second half of next year and into 2016. This is my final slide, and it basically, this is a picture from a place in the Mission District of San Francisco, which is about a half a mile away from the Bayview-Hunters Point neighborhoods. And this is a apartment complex that has 800 kilowatts of solar on top of it, that provisions about 80% of the total load of this entire apartment complex. And this is what Bayview-Hunters Point is going to look like. And from there, the Hunters Point Community Microgrid Project is a model for the rest of San Francisco, the rest of California, the rest of the country, and the rest of the world. So I believe what you're looking at in this picture is a view of what Bayview-Hunters Point is going to look like in a couple of years, and what the rest of the world is going to look like in the coming decade or so. Do you want to take a question?
No, questions at the end. So thank you, Craig. Now, let me introduce the second speaker, Andy Tang. I've known Andy for over 5 years. When I was over at the Electric Power Research Institute as the manager for the Smart Meter program, Andy served as my advisor from PG&E. And Andy and Chris Knudsen, who is also his partner in crime, I believe Chris is now over at Silver Spring. Okay. These two gentlemen did so much for Smart Grid at PG&E. I remember at the time when Smart Grid standards was like herding wild cats. And both of these people were real pioneers at PG&E, talking about the need for having a universal network layer in all of these smart grid applications, whether it be distribution automation or whether it be in metering. And Andy was leading the, what was the program? It's the Smart Grid Technology, Smart Meter Technology Upgrade. And they brought in Silver Spring with the 6 low pan and the IEEE 802.15.4, and really pushed the industry to developing a standard around that. And we saw that in a previous presentation with Phil Beecher with the Y-Sun Alliance now, and how that protocol is coming. So I really applaud you for thinking so many years ahead when people were busy developing proprietary protocols. So with that, I wanted to bring Andy, and what Andy will do is talk a little bit from a technological perspective, as well as some of the market barriers that we are seeing today. And then we'll get into a short break, and then we'll go into Q&A. So I'm just trying to bring his presentation up here. There we go. So Andy, the floor is yours, and you have 25 to 30 minutes.
Great. Thank you, Irvin.
And where's the speaker? Is this the speaker? Okay. Good afternoon, everyone, and thank you for attending. I've been a regular attendee over the webinar over the past 6 years with Irfan's educational series, and it's been very nice to see how he's been deeply committed to this, and it's very nice to see how it's grown over the years, and hopefully these networking opportunities are good for all of us to continue to connect and push the goals of a smarter grid. So my name is Andy Tang, as Irfan just introduced me. I now run business development at a company called Greensmith Energy Management. We are an energy storage technology company, and so we focus on deploying grid-scale energy systems. I think my presentation is going to dovetail very nicely with Craig. In fact, Craig could have given half of my presentation in terms of what we see as the opportunity for energy storage. By way of quick introduction, this picture right here is a 1 megawatt, 3 megawatt hour system that's being deployed in San Juan Capistrano, and the utility that has deployed this system is actually doing this as a T&D deferral. They have a feeder line that is unable to meet the requirements or the demand of the customer that's at the end of the line. And so instead of reconductoring the line, they decided to put an energy storage unit in, 3 megawatt hours, which will allow them to defer that reconductoring exercise for possibly as many as 5 years. So this stuff is real. I'll talk a little bit about some of the barriers, but I'll also talk about some of the positive things, because I actually think, I've been in clean tech for 8 years now, and I'm very, very excited because this is the first time I see a field where the barriers are a lot less than in a lot of other areas. The policy is lining up nicely. The industry participants are starting to line up. It's actually starting to feel like we have quite a potential trajectory ahead of us for the next 5 to 7 years. So I'd like to start this off by just saying that sometimes the past really is prologue to the future. So a presentation that I gave April 23rd, 2009, when I was at PG&E, talked about renewable resource integration. And it said how, I was kind of commenting about the irony that you have a lot of renewables going on the grid, but the problem is that you had to run natural gas in order to deal with the intermittency that came from that from those renewables. However, back in 2009, I said, you know what? Tomorrow, right around the corner, utility-scale distributed storage to back up these intermittent resources and time shift resource availability to be coincident with demand is coming, right? And so this was back in 2009. The costs weren't actually there. Fast forward to 2014, and this stuff is moving beyond the pilot stage and actually into implementation phase. So another variation on the slide that Craig showed us, the grid right now is really straining to support the modern technology. And really, by modern technology, I guess I would really mean the modern architecture of a distributed local grid, right? So traditionally, it's been, very, very, very typical. You have large investments in large power plants. They come over transmission lines into distribution stations and then substations, and then go into homes and go into commercial and industrial neighborhoods. And of course, what we've done to that is we've added wind farms and solar farms on the transmission side. We've added solar and electric vehicles and wind on the commercial and industrial side, on the distribution side. And so all of a sudden, a grid that was really used to one-way power flows of flowing from the desert to the population centers has now become a two-way network with electrons having to flow in both directions. And the grid just wasn't architected for that. So that's the fundamental issue and the fundamental problem we have, and why Craig says there are a lot of fundamental things that we have to get over or that we have to reteach ourselves. It's because the method of the grid's operation for the last 75 years has been one way, from a big power plant to a little home, to the socket in your home, right? And the direction has always been down. And now, with people putting distributed generation on their rooftops, it's suddenly two-way. There's suddenly something called backflow, right? And so what challenges does that create? Well, here's an example of a solar intermittency chart, okay? Real data. So we like to think of solar as a nice smooth power curve, when the sun comes up and around, you may get the highest amount of solar output around 5 o'clock in the afternoon or, 4 o'clock in the afternoon. And we like to think of it as a nice smooth curve. But the reality is, even in sunny California, right, even in San Diego and other parts where it's very sunny, you'll see that the reality is far from the perfect vision, right? So each one of those jagged lines represents a drop from the output that the panel was supposed to give. Now, the larger the field, the smaller this problem, because you have something called geographic diversity. And that's as simple as, clouds are so big, right? And what's the percentage chance that that cloud that's going over is going to block the entire solar field, right? So the larger it gets, the more acres that solar field gets, you get to a point where, maybe the worst disruption would be 60%, 40% kind of output drop. But still, these are some of the power fluctuations that Greg was talking about when he told us to focus on the three things that have to be kept in balance, right? And this is one of the issues that comes about. Another issue is wind predictability. This is a chart that the CAISO put out. I think this was Tehachapi. It's a little bit gamed. This data is a little bit gamed because this was like data in April, and those of you who live in California know that April is a weather transition month for us, so the patterns are kind of between. But the point's well taken, right? The point is that from a generation planning perspective, from the guy who is in a utility told never to let the power go out, this is very difficult to plan around. And so these, I had to show my duck too. Great share this duck. I had to show my duck. Two things come about. One is this is trying to look at the wind profile and the solar profile, and the fact that they happen at different times of the day. And then this is the classic duck curve, which I, like Craig, believe that this is imminently solvable through storage, actually. And some of the work that has been done on the policy circuits, especially with creating something like flexible RA, which is a new product that the CAISO has been working on, is very, very favorable to storage and is very, very favorable to solving this problem actually in a markedly efficient way. So I think energy storage might even be the silver bullet, or might be, definitely is a key part of the solution for how we continue to get to this point where we can integrate more and more renewables. How does it do that? Things that we can solve. Ramp rate control. So this is a big issue, a very big issue in solar, and also an issue in wind. Okay, and this is simply that you have two things. You have in the morning when the solar panel starts going up, the operator, whoever the utility that's buying the power, would like to be able to count on a smooth rate that the power is going up. Okay, and then as it's operating through the day and those clouds come over, again, the operator would like to have that power fluctuation at a more even rate, at a rate where it can actually ramp up other resources in order to overcome the gap. And so energy storage is actually the perfect resource for ramp rate control. You can do this, you can do one-way ramp rate control with solar inverters. What happens is you essentially spill the power, right? But you can't create power, you can't create power when the sun's not there to create the ramp up. So energy storage is ideal for ramp rate control. Energy storage is also ideal for renewable smoothing. This is also called firming. And getting into the economics a little bit, from a developer standpoint, they are paid a lot more money for a firm resource than they are paid for just an energy only or run of the mill or take whatever's produced type of resource. So the utility will pay more if you can guarantee a stable output level, because from their standpoint, it's an easier resource to manage. They have to do less on their end. So the PPAs will generally be higher, and there are mechanisms in place to get paid more for this type of scenario. Again, ideal for batteries. Classic capacity shifting, other names, resource adequacy, proxy for demand response. I kind of call it guilt-free demand response. You kind of, People don't have to stop doing what they want to do, but at the same time can participate in demand response programs. And frequency regulation. So I showed two of the things that Craig told us to focus on. One is frequency, the other is power level. The third is was a little more esoteric for me to show on a chart, but absolutely agree that the interesting thing that people are now starting to get their hands around is that when you put distributed batteries into the local field, you have also put an inverter there. And there's a whole host of functions on bar balancing that you kind of get for free. And what I mean by free is that a lot of people, when they're building their economic cases on how to site storage and how large to put a storage unit, you have to buy an inverter anyway because storage is DC power and the grid needs to be AC interconnected. So you need to do the conversion from DC to AC. So the inverter is sitting there and has to be used. So an additional usage is this power factor correction, or the ability to put reactive power onto the grid at whatever level you need to put it. The added benefit versus just setting the solar inverters at a set point, the added incentive is you can put a CT or a PT clamp on the grid, and you can actually determine what level of bars you need to put on. So you can be even more dynamic. So quick commercial, and I'll keep this to a bit of a minimum. But on the so Greensmith is, as I mentioned earlier, is an energy storage technology company, and we have developed a software platform to help run energy storage systems. We've deployed 35 systems since 2009, which is probably just about the most number of systems behind AES. But we've deployed 35 systems all at ranging from kilowatt-hour scale to multi-megawatt hour scale. And what we do differently, our software layer really is focused on three different layers. One is what I would call the physical layer. And so we connect to various different battery manufacturers, various different PCS manufacturers. This is the inverter. Connect with SCADA systems and other grid market signals. Connecting to AMI systems, since this stuff needs to be measured in a revenue grade manner. And then, of course, the safety measures like temperature sensors, fire suppression systems, HVAC systems within the battery module, within the battery container or building. And then we have developed a computational platform that sits on top of this physical layer. So this is all the operation scheduling, the ability to look at battery units on a peer-to-peer basis, the real-time equipment control, real-time engines to set what happens to the battery. And then on top of that, we layer on a set of applications. And so these applications are how our customers monetize the battery. Interestingly and surprisingly, the majority of our customers right now are not utilities. The majority of our customers right now are actually power developers and IPPs. And so for them, it's all about ROI, right? And so that they have to have a way to monetize. And so right now, we've developed a series of application modules that essentially sit on top of our platform to perform some of the various topics we talked about: frequency regulation, ramp rate control, renewable smoothing, capacity shifting, demand charge management, EV charge management, and black start capability. This is particularly important on islands, by the way, where the grids tend to be very fragile. And I said we were an energy storage technology company. We're technology agnostic. So from the standpoint of PCS integrations, we have systems in the field, or we're deploying systems in the field right now with Parker Hannifin for the inverter, Eaton for the inverter, Siemens, ABB, Solectronics, Satcom, Sungrow, and Power Hub. And on the battery side, we are chemistry agnostic. So we have done a lot of lithium ion. We've done Samsung SDI, LG Chem, Soft, Winston, Boston Power, BYD, Johnson Controls. But we've also done FEOM, which is a sodium sulfur battery, and we've done Vision, which is a zinc ion, and then we're in the process of doing both of these, Vision and Aqueon, which is an aqueous hybrid ion. So I think from our standpoint, our view is that we're not smart enough to know what battery technology is going to be the winner 5 years from now. And in fact, we don't think there's any clear-cut winner. We think that when you look at the roadmaps for all these companies, we're going to be in this state over the next 5 to 10 years where every 9 to 12 months, another vendor is going to come out and essentially leapfrog the performance of someone else, right? And so what we want to do is be able to provide our customers the ability that at a given point in time where they have to make that decision, they are able to use the best technology that will deliver the highest return for them. That's available in the marketplace at that point in time. So why intelligent software? Well, storage is just like solar. So from our customer standpoint right now, what's happening is that the utilities are asking them to go find an appropriate space, go find interconnect to get the permitting, and that they will buy the output subject to some sort of PPA or tolling agreement or some sort of bilateral agreement, right? So they're saying, you take the asset, you take the physical risk, you own the asset, you run it, I'll give you a bilateral agreement, I'll give you some sort of agreement where you get paid for delivering that service. But you deal with the maintenance, you run it, you own and operate it. So in many ways, that feels an awful lot like grid-scale storage. And these are things that people are very, very used to. But storage is nothing like solar at the same time. Two-way communication and energy flows. So all of a sudden, you know, the battery is an energy sink and an energy source. And it actually has to be used in both ways. In addition to that, asset life is highly, highly variable. And I have another slide to talk a little bit more about this, but asset life is highly, highly variable. The world likes to think of batteries as commodities, right? We see this all the time. I mean, you have Duracell, Eveready, and Costco brand, Kirkland brand, right? Everyone thinks of batteries as commodities. But you know what? The reality, at this scale of the game and at this types of dollars of price that we're talking about, where the PPA might be 15 or 20 years long, and so therefore the asset better last the length of the PPA, or you better know what the asset length is going to be. Cell performance varies even within chemistry. So if you have 2 lithium-ion cells, and even 2 lithium subchemistries, lithium manganese oxide or lithium iron phosphate, you will have different performance characteristics because they were manufactured in different facilities and the chemistry is slightly different. First costs are almost irrelevant. This is something that's very, very hard for people to get over. Everyone's all focused on what's your dollars per kilowatt hour. It's almost irrelevant. The battery companies are actually having a hard time getting over this, right? Because if you think about what they're used to a really stupid customer base, all of us. They're used to consumer electronics. When this battery starts performing really poorly, what do? Oh, time to upgrade. 2-year life. These batteries have to last 10, 15, 20 years. So all of a sudden, the battery company is being confronted with, will you warranty your product for 10 years? It's like, did I hear 10 months? No. So, you know, what are those variables and why is software important in this role? Well, you've got to start talking about, like, you know, in utility-like terms, things like LCOE or CONE. LCOE is a levelized cost of energy. And it's a metric that is used across the board, across all different types of generation sources. So you can compare a coal plant, you can compare a nuclear plant, you can compare, you know, whatever resource you want. You basically compare it, and what you do is you basically take all the upfront costs and all the operating costs, and then you divide it by the number of kilowatt hours over the life of that asset that you think you're going to achieve. And that's what your average levelized cost of energy is. And what I'll say right now is that on an LCOE basis, we looked at this for 4 different options. The 4 options we used was a lithium-ion, kind of advanced, premier lithium, expensive, you know, expensive lithium-ion solution, lithium iron phosphate, which is a generally 20% cheaper right now in the market on a first cost basis. We looked at lead acid, which is much cheaper on a nameplate dollars per kWh, and we looked at first deploying lead acid and then deploying lithium ion once the cost curves come down a couple years from now on the lead acid front. And what we found was actually a pretty surprising conclusion, was that in this case, with these particular sets of assumptions, and this is not a universal truth, I want to make that fairly clear, but in this set of assumptions, the most expensive battery actually had the lowest LCOE. So what are those variables that are involved in determining that? Well, the key factors are, first, costs. I mean, they do matter, but they're not the end-all, be-all. Cycle life, how many cycles that battery is going to last. What the use case is. Batteries don't like to be rested, for instance, right? They actually like to be used. So actually, when you think of a use case and you say, oh, let's say I want to do like a demand response type use case, I'll only call it 12 times a year for 4 hours. That's actually not necessarily a great use case, because the rest period, there's almost too much rest period on that. Degradation. So every year, the state of charge, the amount of a fully charged battery drops a little bit. And it drops in 2 ways. There's a calendar life degradation, and then there's also a duty cycle or cycle life degradation. So however you're using it, that accounts for some amount of degradation. And then just the fact that it sits there, even in a temperature conditioned room, just the fact that it sits there, it also degrades a little bit. And resting cycle. So what you're actually doing at rest. And then one more thing I want to talk about on storage is the overall flexibility of storage. What's really nice about it is you could have this whole distributed fleet throughout the distribution grid. And you can have a bunch of scenarios where you need to do it. One might be doing a solar load shift mode for a particular rooftop. One might be in some sort of frequency regulation mode. One might be in a simple grid load shifting mode. And you come in on the next day, and all of a sudden there's an unplanned outage, and you need RA, right? So you can actually flip the use case on all of those batteries and turn them into essentially a virtual power plant, right? Aggregate them, reteam them through our software, but reteam them into an aggregated power plant. Brief commercial. This is a list of energy storage systems that we have integrated over the last 18 months, and you'll see that there are a number of lithium-ion batteries, a number of alternative chemistry batteries, and 6 different inverter companies. And a list of our customers. And that's it. Okay.
Thank you very much, Andy. And as you can see, in the deployment of storage technology to enable distributed energy resources, there are a lot of issues that we need to deal with. And as the manufacturing processes get streamlined, you'll see significant reduction in the cost of these batteries. At the same time, we have to think of it from a sustainability perspective. I'm glad that Andy brought up this levelized cost of electricity metric, because in that we also have to start including the environmental impact of the entire life cycle of all these renewable technologies. Just like we do with nuclear power plants or with coal plants, we have to think about all the streams in China and other places that are getting polluted from the production of a lot of these things, where the environmental rules are not as stringent. In large scale, they will not be able to do it because it will start impacting the quality of life. So it's important to have a proper metric on the ecological damage that occurs from all sources so that we have a true apples-to-apples comparison. There is no free lunch. Basically, that's what it comes down to. So while we see scientific innovation as helping streamline manufacturing processes, bring better chemistries, we have to keep that overall picture in mind. Now what we'll do is we'll take a few minutes, kind of like a break, a breather. We're going to start in about 5 minutes again. So this is planned just so that we can regroup here. And what I'm going to do is I'll pause the recording and then resume it again. So we have 5 minutes. We're going to start at 1/4 off. Thank you. Welcome back to the Smart Grid educational series for October 2014, live from UL in Fremont, California. I'd like to thank Barbara Judge and Richard Hammer of UL, who have kindly hosted this seminar and provided us a delicious lunch. I'm sorry for those of you who are online, we have not reached that level of technology where we can turn these food bits into real bits and send them over to you. But I'm sure you will trust us in enjoying these on your behalf. All right, so now for the next portion, we've been talking at the high level with Craig's presentation about markets and about initiatives at the state level and at the local level. We had Andy come and talk about opportunities in the space from a technological perspective, as well as from this information layer perspective. So I'd like to just say something for a minute or two before we bring Bernie on. It is really important to have that information/computational layer in this business. And when I say that, I have to say that the need for standards or use of standards is very important in order to develop a healthy information/computational layer in this business. The challenge that we're facing right now is if you look at all the standards that are touching this, you've got Zigbee Alliance with their smart energy profile. That has a touch point with this space. You have IEEE with 1547 with .1, .2, .3, goes all the way up to .8. So you've got that standard. You've got IEC 61850 Lite, L-I-T-E, which is essentially the -7-420 subdivision of the IEC 61850 that's focused on distributed energy resources. And then you've got the industrial controls protocols like Modbus, BACnet, OPC, and so on. This is the epitome of what I call the wild, wild west. And you can't just have a sheriff come into town and take care of this wild, wild west. What this requires is systemic thinking. There is a place for all of these protocols to exist. There is a need for defining proper interfaces where these protocols talk to each other and exchange information. And there is a need for vendors like Greensmith to come into the space and demonstrate the interoperability of these various protocols by being able to provide the right interfaces to all of those protocols. So while each vendor in this space can have their own proprietary computational algorithm, and that's where they will compete one with the other and have the better GUI, the more user-friendly aspect, but there is a need to have standardized interfaces for data exchange. And so I'm going to encourage all of you who are online, as well as those in the room, to participate in these standards development processes in IEEE, IEC, the DNP user group, the Zigbee Alliance, OPC, Modbus, BACnet with ASHRAE, all of these entities to make sure that all the pieces of the Lego come together and form this. Because the biggest tragedy in this space would be that we all create a bunch of towers of Babel that start going and hitting each other. And it makes it very difficult for a vendor like Greensmith to operate in this space if it is highly siloed. You're going to end up with the S-curve top coming very soon in this business if you don't have standards. So we made a big hoopla about the Internet protocol, and I love that. And that brought at least the comms layer together. But the application layer with the object models, well-defined object models, is needed in order to have a modular approach. So think of it from this perspective. If you're a utility and you can be vendor agnostic, wonderful. That helps protect the customer, the end customer. If you're a vendor, you can build as you go. You have a very modular approach to your product because you have standardized interfaces. And if you are a customer, you can go buy products from the market, stick them in, and be a prosumer, as Christine Herzog would talk about. That modularity will be there. So the reason why I'm saying all of this before Bernie comes on is because Bernie works at the layer where fantasy meets reality. And for fantasy to meet reality, standards is part and parcel of that. So I want to now welcome Bernie, who's going to talk a little bit about what standards we'll need around the installation procedures for storage and other distributed generation, what kind of training would we need around those standards, and then whatever else he feels like talking about that he hasn't shared with me. So with that, Bernie, and there's a little bit of a jump here. All right, so this is your speaker. And you can just do page down and move from one slide to the other.
Page down?
Yeah.
Okay, great. We may not have those out or not in the middle. Well, thank you, Irfan, and thank you everyone who's here to listen, and everyone who's on the internet participating in this webinar. So I would like to talk to you about the case for energy storage standards, training, and certification. My name is Bernie Kotlier. I work for the California Labor Management Cooperation Committee. And the subject matter for today is going to be a few questions which Irfan asked me to pose and answer. One is, how do we create a culture of performance, efficacy, and safety? Another one, what is the role of standards, training, and certification? And that's going to be narrowly defined today, really as installation, maintenance, and repair. I'm not going to get into interoperability and communication standards. There isn't time for that, and it's really not my forte. And then how do they enhance or diminish the market health and growth? And I'm wondering, well, what does this guy know, and why is he the guy who's speaking on this subject? I'm not going to go through my whole bio, but there, and it's on the web for people who are interested. But I've been doing this for the electrical contracting industry for 7 years, and I'm in charge of all their training and education, market development for sustainable energy, and that includes the National Electrical Contractors Association and the IBEW, the electrical workers. I'm on a number of advisory boards to the PUC and the State of California Schools Future Initiative Advisory Committee. I'm on the board of the California Clean Energy Fund and CalCharge, and on and on. So you can look at the detail if you wish. So particularly though, I think my experience in recent years relating to this subject has to do heavily with two organizations that I co-founded and co-chair. One of them is the California Advanced Lighting Controls Training Program, or CalCTP, and that's the website, calctp.org, if you want to know more about it. And another one is the Electric Vehicle Infrastructure Training Program, and that URL goes to the Department of Energy and the website there on that training. I co-founded and co-chair both of those organizations and some others as well. The model for these organizations is broad participation by the industry, and they are for the industry and of the industry, meaning we want everybody involved, everybody participating, contributing, and benefiting from these organizations. They're nonprofits, and they are brand neutral and agnostic, contractor neutral and agnostic. And we have significant volunteer activity in them. So why is this important? Why is this question of standards and safety and all important? Well, we feel that it's extremely important that we develop a culture of not only performance and efficacy, but safety in all of these areas of emerging technology. This has not always been the case. Certainly there's been a focus on efficacy and performance in many of the new technologies, but safety is not always there. Often we see industries focusing on a band that runs from innovation to commercialization, as if commercialization is the holy grail, and once we get there, once somebody sells the product, we're done, we're successful. We hear talk about the valley of death. Well, the valley of death is someplace between R&D and commercialization in most people's minds. But what I'm going to show you today is that there's another valley of death, and it has to do with that last step, getting that product installed and performing properly. Another issue is cost. Very often new technologies are expensive, and so to get them to market at a competitive price, there are corners cut. And we're going to see where some of those corners have been cut and what the consequences are of cost-cutting at late stages of the implementation of the product's operability in the marketplace. So a few lessons for you from history. Solar thermal. Most of you are technically inclined. Many of you probably know that PV solar, which is very popular today, and we've heard a lot about it already, is only 15 to 25% efficient. Solar thermal, solar hot water heating, is 45 to 70% efficient, roughly 2.5 times more efficient. What are the relative market shares? Well, PV solar is killing solar thermal. Solar thermal is very small market numbers in the United States. Not so in other parts of the world. Why is this? Well, for those of you who remember, in the late 70s and in the 80s, when solar thermal became popular, when solar meant solar thermal, there was a gold rush, Wild West mentality, just as Irfan was talking, and there was no sheriff in town. There were basically no standards, there was little training, quality control was almost non-existent, and what did we get? We got very poor performance. We got equipment that leaked, we got homes that were damaged, we got a very, very negative response from the market and a negative image in the marketplace, and that has almost killed the solar thermal industry. And that is probably the main reason why, even though it's much more cost effective and much more efficient, we see much less of it today than we see PV solar photovoltaics. Some lessons from the electric vehicle industry. Now, I have to admit, this photo is a little bit overly dramatic, but it does wake up those who are napping after lunch. Is it crazy? Well, actually, even though it is dramatic, it's not so crazy. So, anybody know what this photo is? Well, if you look closely, what you'll see here is a Suzuki Samurai and a Chevrolet Volt. This is a garage in Connecticut where they were both burned down to their skeletons. Why? Well, if you read the headline, it said the Chevy Volt had something to do with it. In fact, there were a number of these fires, not only in Connecticut, but in North Carolina, Texas, and other places. And in every case, more than 2/3 of the headlines either blamed or associated the Chevy Volt with these fires. In every case, the fire marshal later said that the Volt was not the cause of the fire. Now, that second line is a little bit hard to read on purpose, because page 42 is a lot harder to read than above the fold on page 1. And that's what happened. So even though the Volt was not ultimately the cause of these fires, it got blamed for them, and the image of the electric vehicle suffered tremendously. So how did this happen? Well, the automotive industry, like most industries that have an emerging technology, focused on that innovation to commercialization. And they either forgot or ignored that last step of what happens when you actually install and maintain. The Society of Automotive Engineers, SAE, was not even fully aware that when you install charging stations or electric vehicle supply equipment, that it is the purview of the construction industry, the electrical construction industry, to do this work and to set those standards. They spent about 2 years trying to set standards for the electrical construction industry before they found out that it wasn't their area of expertise. Cars were expensive when they first came out. They're still expensive. What did they do? They tried to squeeze costs out of installation, charging stations, and that final area of implementation. There was no training initially, and no standards, and no requirements for electricians to do site assessments or load calculations. The reason for these fires, oops, wrong one. The reason for these fires, no site assessment, no load calculations. Wires overheated. Now some of you are going to say, well, breakers should protect it. Well, they don't. If the breaker's too far away from that hot wire, it doesn't flip in time. If the breaker's not exercised annually, it might get stuck, on and on and on. Breakers don't protect you every time. So site assessment and load calculations will, if people are trained to do them. They weren't. That was the story. Some more images from the energy storage industry. File, October 2007, Matsushita Battery Company, battery plant fire in Osaka. This is not the actual photo. I couldn't find the real one, but it's close. It's good enough. It's a factory fire. That's what happened. Now, this one actually is the real photo. I was able to find this one. This was at LG Chem in 2008. $85 million worth of damages. Production halted for more than 2 months. These were not private images. These were in the papers. These were on the media, on the television. Massive global recall of laptops. More than 7 million units made by batteries made by Sony Corporation. Affected Sony, Fujitsu, Dell, Apple, HP, Lenovo, and Toshiba brands. Seared in the public image. Oh yes, the Dreamliner. What happened to it? It became the Nightmare Liner. Headline, Dreamliner jets grounded, battery failures, battery fires. More images, not the most positive. Well, have we established the value of doing things right, doing them safely? Does it matter? Will an industry's success turn on whether we do it right, whether we have a culture of safety, whether we have training and certification? I hope so. So how do we create a culture of performance, efficacy, and safety? Well, first of all, we must build an awareness of the need and the critical importance of this because, frankly, that innovation to commercialization is too often the mantra of our emerging technology industries, and they just forget that last step. We need to rally our industry and support and participate in this. We need to establish standards. Now, it's true, interoperability and communication and others are important, but I want to talk to you today about installation, testing, maintenance, repair, and retrofitting. We need to utilize industry institutions and platforms and processes that are available. And we need to understand what industry it is. A lot of emerging industries, especially high-tech ones, think that they're new and they're going to create all of this from scratch that it doesn't exist. Well, the wake-up call for everyone. This is electrical work. It's done by the electrical contracting industry. They've been doing it for over 100 years, and it is electrical construction work. And there is a safety system in the electrical contracting industry. It includes 3 essential components: product standards, installation codes, and electrical inspection. And I don't care how new or different your energy storage system is, it's going to have to be installed, it's going to have to work properly, it's going to have to be safe, it's going to have to be inspected, and have to be permitted. It's part of the electrical system. So, what are some of the components of this? Well, we're talking about them here: codes, standards, inspection, enforcement. Something important that we're going to get to is how we get these qualified contractors and electrical workers into this picture. That comes with training and certification, which we're training and certification of them, which we're going to get to in a few minutes. But it takes all of these components and all of these steps in the process to get to safe products that work properly and protect the image of an industry so it can grow and prosper. Standards offer benefits to all segments of the business and industry, public and private. They allow us to get lower costs, to avoid duplication, to be compatible, to interoperate, all these things we talk about. And they've also helped advance scientific discovery and protect environmental resources. So there is something called the National Electrical Industry Standard, the NEIS. What is it? It is a standard that was first developed by the National Electrical Contractors Association. These standards are in various areas are continually published by NECA, the National Electrical Contractors Association. There are a series of quality and performance installation standards for electrical products and systems, and they extend beyond minimum installation and safety requirements of the National Electrical Code, or the NEC. So they're more than just basic safety code requirements. The National Electrical Contractors Association was formally established in 1901, so it's over 100 years old. NECA is the voice of that industry. There's 119 chapters in the U.S. and abroad. The Codes and Standards Committee is made up of 38 members from NECA companies. They represent NECA on all 19 code-making panels of the National Electrical Code. They chair 6 of those panels. NFPA 70E, which is the standard for electrical safety in the workplace, is part of that. National Electrical Safety Code, or the NEC, is part of it. And other NFPA codes like 90A, 99, 72, and 79. And don't ask me what each one of them are. But I can tell you that they're all part of what NECA and NEIS does. So use and conformity to the NEIS standards is generally voluntary. It can become mandatory, if they're incorporated by references. And they're available for use and specification by all parties, not intended to be exclusive. The purpose of the National Electrical Industry Standards is to define a minimum baseline for quality and workmanship. And they're intended to be referenced in contract specifications and documents for construction projects. Most of energy storage will be involved in construction projects, electrical construction. These standards are written and developed by subject matter experts, by SMEs. They're reviewed and voted by industry experts, and there's a strong and balanced participation. Once the consensus is reached in industry, the standard is then submitted to ANSI. I think most of you are familiar with ANSI, the American National Standards Institute. NECA is an ANSI-accredited standards development organization. Okay, so how do we get to the National Electrical Code, the NEC? Well, first of all, I think most of you know that the National Electrical Code is the basis for the electrical code in all electrical construction in pretty much every state, county, and city in the country. This is the Bible of electrical safety and how to install electrical equipment. The NEC provides a minimum standard for safe electrical installations, and the code and NEC are produced and registered by the NFPA, the National Fire Protection Association. So the relationship between NEIS and the NEC is that NEIS, those standards are performance standards to ensure quality and workmanship. They clarify what's required to perform neat and workmanlike electrical installations. Supplements to the NEC, they supplement the NEC by including the minimum requirements for quality installation. The standards are not the code, but the standards flow into the code. The code, the NEC, is a safety installation standard that is a regulation that is required, as I said, just about in every state, county, city, and town in the nation. So the standards are performance installation standards. They're for receiving, storing, and protecting material. They're for burn-in, testing, and commissioning. They're for the orderly turnover of a project to its owner. They're for maintenance and repairs. And they're for all kinds of adverse circumstances, faults, floods, etc. There are approximately 8,000 volunteers who serve on the NFPA technical committees. And those technical committees and panels represent a variety of balanced interests throughout the industry. There are approximately 200 different technical committees and panels that are responsible for development. This is, what we're telling you here is this is a very old, established, and very thorough process to get these standards. So once again, for those people who are coming in new, the electrical industry, and think they got to create all this stuff, it's there already. So, continuing this question of how do we create a culture of performance, efficacy, and safety? What do we have to do? Well, first of all, we have to refocus that industry mantra of innovation to commercialization and change it to one where we are talking about innovation to installation. We've already talked a little bit about standards. The second and third key factors here are training and certification. And for those programs to be effective, they must be open programs to all licensed or certified electricians. These are not programs just for NECA members or just for one group or another. These are industry-wide open programs to everyone who's licensed or certified who can take the class and pass the test. So the content of training of this type is based on bringing the energy storage industry and the electrical construction industry together. And the electrical construction industry is aware of that. The paper that was just handed out to you came from a workshop that was done at the storage conference just a few days ago. And everyone was invited, as are you invited. And you can see on the bottom of that sheet how you can contribute to this process if you are interested. There are contacts there. So what we're looking for is stakeholder participation and contributions to the NEI standards and the National Electrical Code requirements as they are updated on a regular basis, particularly in the area of energy storage. What will the training curriculum development look like? Well, first of all, it will be based on a curriculum that is founded on the NEIS standards. It will incorporate the National Electrical Code. Every electrician who's going to install energy storage equipment is going to have to be absolutely knowledgeable and be able to pass the test on what are the requirements to install that equipment safely and effectively. We'll use modern techniques of blended learning. There'll be web-based introductory prerequisites. It'll combine lectures and, most importantly, hands-on training components for training the electricians who are going to do this work. Training and certification must be comprehensive and rigorous. This is not going to be done just to throw a piece of paper out and say, you know, you can do this in a few minutes and get your certificate. Those who are certified are going to absolutely be qualified. They'll be certified by demanding exams, and the whole program has to be administered by a third-party, arm's-length organization. It will, as I said, be brand neutral, contractor neutral, and nonprofit. And the model for this is the California Advanced Lighting Controls Training Program, calctp.org. Here's a screenshot of the home page and a little bit about this organization. It is the model because of its success. It was founded about 6.5, almost 7 years ago. The stakeholders in this group represent the kind of stakeholders we're talking about for energy storage training. All the major utilities are members of CalCTP, the University of California, the Cal State Universities, the California Community Colleges, 14 manufacturers, the National Electrical Manufacturers Association, the electrical workers, the contractors. Pretty much everybody who's involved with advanced lighting controls is part of CalCTP. And CalCTP has a rigorous curriculum, comprehensive, and as you can see here, hands-on training. It has trained about 2,500 electricians to do certified installation of advanced lighting controls. Why was this done? Why was it necessary? Because at the founding of CalCTP, the utilities said they had spent millions and millions and millions of dollars on incentives for lighting controls, and they weren't being installed properly, which meant they weren't working properly, which meant people weren't getting their return on investment that they expected and deserved. And that's a problem for the taxpayers, the ratepayers, and the investors in the properties. CalCTP contractors and electricians who graduated this program have done a fabulous job. There are virtually no complaints when a CalCTP contractor or electrician performs an advanced lighting control project. It's been an absolute success, and that's the reason it's the model for what's going to be done in energy storage training and certification. So this organization is just getting off the ground. Some of our initial members who are taking part in getting the new training and certification for energy storage off the ground are the NFPA, the National Electrical Industry Standards Group, CalCEF, the California Clean Energy Fund, CalCharge, which is a trade association for energy storage companies, which was launched by the DOE and the Lawrence Berkeley Lab and the Stanford Linear Accelerator Lab, of course, NECA, and the National Alliance for Advanced Technology Batteries. All these organizations are involved in the ground floor. More are welcome. That's it.
Great. Thank you very much, Bernie.
Thank you.
And as people online and in the room formulate their questions, we'll go up to about 35 minutes past the hour, so we have a good solid 15 minutes to ask questions because a lot of you have waited patiently for questions. Now, Andy had to leave. He had another scheduled appointment, so he had to go. But we have Bernie and we have Craig, and if there are questions for Andy, all you have to do is email them to me, and I'll send them to Andy, and then I'll do a group response to everyone so that you all can see that. And what would be really helpful is for those who are in the room, if we could just have a sign-up sheet, you know, with just your name and email address, just so that I know. I know some of you have registered online, but I want to make sure everyone is covered. And then we'll start with the questions. So let's see here how we're doing on the chat window. All right, and then we'll open the Q&A. All right. So we have, okay, so there were some questions, first of all, from a logistical perspective. You all will get the presentations in PDF, and you also get the link for the webcast recording. So that's going to happen. We have a question here. I'm going to repeat your question for the purpose of the online, or you can just walk up here either way. Go ahead.
A question for Bernie that he mentioned California lighting technology, lighting control as what's being used for the energy storage. And does this lighting control have anything to do with battery storage specifically? No, it's only the organization.
Okay, so let's, for the purpose of the people online, the question was the link between the California Advanced Lighting Program and electric storage. So Bernie is going to clarify that point. So Bernie, if you could just come close to the phone.
Sorry that I had to rush through that and it wasn't clear. The model is the structure of the organization. Industry-wide, nonprofit, brand neutral, with a lot of participation from a lot of stakeholders. Really has nothing to do with the content. It's all about the model, structure.
All right. So are there questions online? Yeah, please post them in the chat window so I can have a look. And other questions in the room. So Ronaldo, you have a question?
Yes. The comment that you made, several of you made, about rush to commercialization was repeated in a number of ways, including your presentation. Is there training for recycling batteries, storage systems, as much as any other product that we have not approached in the industry as we should?
Bernie, could you repeat the question and then answer it?
Yeah. I'm not sure I'm the one to answer it, but I think the question was there was a lot of talk about the rush to commercialization, and the question was, is there planning and is there training and education for the recycling of energy storage devices? And I'm not sure I'm the one to answer that. I mean, I hear things about recycling, but it's really not my core competence.
Right. I will say this much, that because we are in the infancy of this industry, it's still a lot around design and installation. But people are thinking not only about discarding the batteries, but also secondary markets where these batteries could be used. Maybe in a future of battery to grid kind of system where you could have localized areas of that resource available, because you don't need that high performance necessarily. Sometimes you need bulk energy and storage.
What I can add to that is that there already is a lot of work on reutilization of electric vehicle batteries to go to facility-based energy storage or on-site energy storage, because when you get down to about a 70 or 75 or maybe even 80% density in that vehicle battery, it's going to be replaced. But 70% is probably still very usable facility or on-site storage capacity for a number of years. So there's certainly some discussion. Some actually.
And I'll add on a little bit here too. Right?
It's to hold so that I can hear you.
Taking a phone call. So I think what the two gentlemen just said is absolutely accurate. There is a second life for at least the vehicle batteries, but in terms of the recycle plans for some of the larger installations, what I will say is that there's a lot of value built into a battery and a lot of recyclable value. So when you look at just a regular car battery, the vast majority, like 98, 99% of regular car batteries are already recycled. The value of one of my cars is a Prius. Even that battery is significantly more valuable than just a regular car battery. The likelihood is that those are going to definitely be recycled. So the higher the value of the original cost, the higher the value of the materials, far more likely it is to be recycled.
All right, so we have some questions here online, and then Pete will get you one sec. The question asks, would the microgrid at Hunters Point be a distribution microgrid owned and managed by PG&E?
The answer to that is it's still to be determined, but I think it's actually going to be a mix. If you segment the market, and the Hunters Point market is the same as any other urban area, you've got a mix of residential and commercial and industrial customers, and what I see here is that you have multiple market segments on the renewable side. You've got the residential, you've got commercial, and then you've got kind of the grid, which would be the utility as the customer. And then on the intelligent grid solution side, these would be solutions that are the batteries and the demand response programs and advanced inverters, et cetera. It would be a lot easier if PG&E agrees to own those assets, at least here in the initial instance where we don't really have monetization opportunities that are very mature in California. And again, the way I describe the difference between procurement, which would be the utility buying those solutions, versus monetization, which is where either the utility or a third party would own those solutions and then monetize them through our open market monetization mechanisms through CalISO. You've got to have those markets at CalISO available in order to monetize, and CalISO doesn't really have very much to offer yet. PJM, which is it's a CalISO type organization out on the East Coast, they're much further along in terms of developing the markets for frequency balancing for sure, and I think even voltage balancing, and a very major demand response program monetization opportunity. So CalICE is a little bit behind, but I'm not digging on them because I'm not criticizing them. This is complex stuff. It's new, and I think they're making a really deliberate effort to resolve that. But for right now, and we want to build out Hunters Point next year, and starting middle of next year out through the end of 2016, we want to be done by the end of 2016, completely built out. The only way that's going to happen in the time frame, in the given time frame, is if the utility owns at least the larger installations.
Pete Shoemaker, you have a question in the back?
Yes. So that solar and distributed resources can put off or defer grid maintenance. Maybe some value there. Is there any way to think about targeting areas of the grid to incentivize solar, using that potential?
Absolutely.
Craig, repeat the question.
Yeah. Okay. So the gentleman asked, is there a way to structure compensation? You used the word incentives, but I'm just going to use the word compensation because I made a very big point that location matters. And location matters because it's more valuable to a ratepayer in certain locations than it is in other locations. And we need to match the value to the ratepayer to the value that we're willing to compensate the people who bring the solutions. So the Clean Coalition has done a lot of work with the Long Island Power Authority in New York. And that's now managed, the LIPA service territory is now managed by PSEG Long Island, and we're working with PSEG Long Island. We helped them design their feed-in tariff program, and one of the big elements of their feed-in tariff program was a pretty sizable premium for solar projects that were deployed in the South Fork of the East End, which means the very tip of Long Island, which is where they're at the end of the feeders. They have the most vulnerable grid infrastructure there, and they needed the renewables. They needed generating capacity to get deployed there, and they determined that the value to the ratepayer was worth $84 million of deferred infrastructure investments in the form of transmission and central generation. And if they got 40 megawatts of solar there, if you divide 40 megawatts by $84 million, that's over $2 a watt. That pays for the solar by itself, right? You can install solar for $2 a watt nowadays in larger chunks. So yeah.
Because the variability is first, can it depend on that, or can they not? They have to have some kind of variability with storage to be able to budget right.
Yeah. So to date, I'm not aware of any. In the case of Long Island, they would be happy to extend that same concept into the battery game. We didn't do that yet. We're going to do that. We just actually worked with PSEG Long Island to update their Utility 2.0 plan. And on page 19 in that plan is discussion of how the Clean Coalition and PSEG Long Island are going to work together to site some energy storage out there in that same part of the grid. So yes, we can do that.
Right, along that line, for peak periods, the peak period might be targeted for some solar. Is that policy or any movement on that here?
In where?
In PG&E, sure.
In PG&E. So the question is, do we have that same benefit in PG&E? There's a lot of discussion in California around locational value. There hasn't been a implementation of it yet. So that's, shame on California, right? That we should be ahead on this because everybody knows that there's value there, and we've all been arguing about how much the value is. But I think we will get there if we can get the CPUC to kind of, really take a concerted effort on it.
I have a logistical challenge. I promised 2:35, which means I have 4 minutes for 4 questions. So we'll be really, really brief now. Craig, really briefly. Conventional generation is naturally slow to respond to changes in transmission operators' work to maintain stability. Is there a stability concern with faster responding distributed power electronic devices? who assures that they do not get unstable?
Well, ultimately the operation of the grid is that responsibility falls on CAISO and the utilities in California. So, and I assume the question was in California. So it does remain the responsibility of those organizations, and I'm not quite sure what the reason for this question was. It could have been to say that the utilities in CAISO have a big responsibility, and that's true, they do. So we've got to make sure that whatever we do in terms of transitioning to this new energy future is bringing reliability and power quality, and that's why projects like the Hunters Point Community Microgrid project are all about showing we get to high penetrations of renewables while maintaining or enhancing grid reliability and power quality. But at the end of the day, the responsible parties will remain the same. It will be CAISO and the utilities.
Great. That was Ray Hayes, who was formerly with AEP, who asked the question. Okay. Michael Shea asked, would there be a mechanism to request the battery manufacturers to disclose the characteristics of the batteries, like the processed foods industry disclosing the characteristics of the foods for sale? In other words, the 11 herbs and spices.
Well, I think that it was actually Andy that went a little bit more into the details of, how you can have slightly different variations of chemistry mix and get very different results in terms of the performance of a battery. So I think that, battery manufacturers are going to be somewhat reluctant to give away their exact chemistries. But my guess is that it's probably more like semiconductor processing, and that it's the process that is actually more important than the exact chemistry. So whether it's mandated or not, maybe if they have any toxic materials in there, they should be disclosing that. But I think that's already disclosed. Yeah. It's not the exact mix is not disclosed.
The short answer is that the Environmental Protection Agency sets rules on all kinds of hazardous materials. So batteries would come under that. There are 3 or 4 means by which a battery can interact with the environment. One could be leaching, like in water systems. Another could be aeration. Things could land in the air, or it could mix with the soil. So all of those require standard EPA guidelines, just like any hazardous material. Batteries have to be seen as material that is hazardous. I mean, if it's ingested, or if animals, or if it goes into the marine life, it will affect. So you don't have to think about it as a technology, but rather as a set of chemicals. Each company will have to respond to the EPA of their state to meet those requirements. So I don't think anything special is going to happen just because of batteries. The other thing is about it is the need for standards here. Again, it's very important that the safety issues that Bernie brought up need to be followed. From a fire prevention perspective, they need to be following what the Fire Protection Agency is putting as code. So those kinds of things are the general strokes of the paintbrush, if you may, that all these vendors will have to deal with. Next question, Ray Hayes asked, is anyone employing synchrophasers technology for monitoring and control of distributed storage systems? I know that there is no physics reason why they cannot be used. I know that for a while cost was an issue with synchrophasers, that they were really expensive and they made more sense at the bulk power system. But if so much energy is going to be generated at a distributed level, at some point it makes sense to have them at this level too. So Craig, you want to?
Yeah, I can't claim any deep expertise on synchrophasers. I am somewhat familiar with them, but not an expert. And I am hearing more and more about them because I think that they indeed can play a significant role in the monitoring, communication, and control piece of the solution. And as I had stated during my presentation, the way that you coordinate, the way you get value out of distributed energy resources is you coordinate them. And to the extent that synchrophasers play a role in that coordination function, then they can be very valuable. And as I understand it, synchrophasers are primarily used for frequency balancing, and frequency balancing is one of the primary grid services. So yes, synchrophasers can play a big role. It's just going to come down to economics and do they make more or less sense than some of the other ways of monitoring frequency.
So one of the ways, I mean, part of the need for synchrophasers is, of course, grid stability. But I'm also thinking that in the distributed model, these could very well be enforcers for service level agreements between the various service providers at the distribution level. So if I have a battery or I have a microgrid and I'm offering electricity onto the grid, how nice a way to use synchrophasers as a way to show that the electricity that came from a certain place met certain power quality standards so that it could be monetized. Because what Andy showed us is what people don't want is cruddy electricity, that goes up and down really fast. So nice, smooth. And synchrophasers with their short time scales can show that level of granularity to the tune of as much as maybe 200 samples per second. So you could see how good the quality is. All right, so next question is, Michael Shea says, would there be a mechanism established to have privately owned, operated, and managed microgrids be checked up for its fitness like the regular smog checks for cars in California? Wow, he's really thinking way out there. Okay.
I'll just say that there's a group, and the name of it is escaping me at the moment. John Kelly and Kurt Yeager, Kurt formerly with EPRI, have formed this organization. It used to be called Galvin Electricity Initiative, and they've got a new name, and they've got a standard called PEER, and I've forgotten what the PEER P-E-E-R stands for, but it's all about having a standard for the quality of an electricity system, and so I think it does make sense to have a standard around it. I don't think it's going to be managed in the same way as the smog check procedure, but basically, people, it's pretty well known when there's a grid disturbance, and grid reliability metrics are already very well documented and reported. That grid reliability metrics have to exist for 5 minutes or longer before you actually have anything that's considered to be a reliability issue. But power quality issues happen in second level ranges, and I think we do need to bring we need to bring power quality metrics into our standards, and so that's something that we need to needs to happen in the future.
Great. So at this time we'll conclude the questions, and just some concluding thoughts. As you've seen in the last 2 hours and 10 minutes, that distributed generation is here to stay. Storage is a critical component of that, but in order to have mass market appeal for this technology, it's really important to observe standards at all levels. There needs to be regulatory policies that are conducive for distributed generation. Andy and Craig share hope that that regulatory framework is moving in the right direction. The technologies have to be there, and Andy's presentation showed several players in this market, and Greensmith remaining relatively agnostic to the technology as a way to enable real solutions. And then Bernie's presentation showing the need for safety and to have standards at that level. Ultimately, this business requires the private sector to invest large amounts of money and be able to see the return on investment. This is not something that happens with thousands of dollars or hundreds of thousands. This is millions of dollars. This is billions of dollars. The important thing for the private sector to understand is realistically what is the return on investment. And as I see the consumption of electricity growing in the United States and the supply of centralized power diminishing, I don't see any way but this way for the foreseeable future. Even if I wanted to build a nuclear power plant tomorrow, it would take several years for it to get commissioned, and then even then it will not address the peaking problem. It will not address the congestion problem on the transmission line. So there are several issues around that, even if we got over the political pressure against it. So it's really important for us not to remain in a dreamlike state. We have to wake up. Bernie showed us some pictures to wake us up today with some fires, because fire has a way of waking people up, even in the middle of the night. They smell it, they wake up, they run out in their pajamas. So I'm not suggesting that we have to run out in our pajamas, but be proactive and get involved in this industry and not wait till the 11th hour when haphazard solutions are promoted with questionable technologies and business processes. This was an opportunity to open your eyes and ears to a new way of looking at things. We got some pioneers to talk to you about it. I'm really, really happy that you all participated. Our next seminar is going to be on transactive energy. I've scheduled it for October 29th, and I will be sending out reminders of that. And we will have Ed Cazalet from TMIX speaking about it, and also Mark Knight or someone from the Gridwise Architecture Council to talk about transactive energy. So if you think about it for a real quick moment, transactive energy is really necessary to create some stability in the pricing market. If you don't have transactive energy, in other words, you set a contract with your service provider to get a certain amount of electricity, and if you use more than that, you only pay for the incremental amount at the real-time price, or if you're using less, you can sell that additional amount that you have in real time. So that really helps stabilize the supply and demand for electricity. If you just leave it purely on a real-time pricing way, demand response applications, it can get very unstable. So transactive energy gives everyone something around which they can plan. I hope you can participate in that very important webinar. And then in November, on I believe the 5th of November, we are going to have a presentation on electromagnetic compatibility. With all of this that is going on with wireless communications, EMC is going to be very, very important going forward. So thanks again. I know we ran 15 minutes over, but I hope it was well worth your time. And with this, I'm going to end the recording, and then we will be sending out the presentations and recording in the next couple of days. So have a wonderful afternoon and enjoy.